the last section, I described the service of HMS Broke during the First World War, focusing on her role in the Dover Patrol and specifically on the Battle of Dover Strait in April 1917. I included information on her captain, Edward Evans, and my family member, able seaman Joe Bagnall. It was knowledge of this story, including further examination triggered by the 100-year anniversary, that motivated me to build the model. It was my first ship model. I will describe the process of construction and some of the learning therein, including a few of the trials and errors along the way. I knew that I wanted a working model. Being more naturally software rather than hardware oriented, I looked at 3D printing instead of the more traditional wooden hull build. Desk-based research revealed a relatively limited number of pictures of the actual ship, many of which were shown in the previous talk. The most helpful plans were the 1:48 builder's plans at the National Maritime Museum in Greenwich. There is a special pleasure in handling the originals, and the plans department were most helpful. I attempted to stitch together a set of pictures that I had taken to make a usable plan, but then decided to buy a digital copy. It was a little pricey, but well worth it. One key element that was missing was the lack of hull lines or cross sections. There were a number of sectional drawings, but not enough to work from. A trip to SS Great Britain in Bristol located a plan of sister ship HMS Tipperary in the MacGregor collection, drawn for modelers and with very helpful cross-sectional hull lines. This was essential data. I didn't have 3D modeling or printing knowledge at the outset. Clearly, modeling the hull was going to be critical. I eventually found a most helpful article on the Nautical Research Guild's Model Ship World forum that described step-by-step hull modeling using the Blender package. Invaluable. I bought a standard Ender 3, an entry-level 3D printer that gave a good start point. I'm guessing that the process of hull modeling is one of the steps of most interest, so I will go into some details. To set up the hull modeling, the plans of the ship are imported into the 3D space, scaled and oriented, much as one would for a physical model. Then, a regular grid of points or vertices is created and overlaid onto the hull. Next, the vertices are aligned along the length of the vessel to match the placement of the cross-sectional lines on the plan. So each vertical line of points is aligned with the hull cross-section. The lines of vertices matching each cross-section are selected in turn, and the individual vertices moved outwards perpendicular to the plan in order to fit the hull line. As the orientation changes, you can have seen that some of the sets of points towards the stern have been matched to cross-sections, and then looking from the stern, the individual vertices are visible directly on the corresponding hull line. Moving on, all of the cross sections have been modelled, surplus vertices removed and some added, for example at the transition between the foredeck and the main deck. The hull is taking shape. Also note the addition of the overhead plan view. The vertices form a plane, which is shown in grey. Some smoothing takes away the angularity. And finally, a mirror reflection starts to give a recognizable hull shape. There are still noticeable imperfections in the modeling process, but it's getting close. The vertices on the hull lines continue to underpin the model as the hull is refined. The builder's plans have now been added to the model space. With additional smoothing, both manual and by algorithm, the hull is much smoother and more precise. In addition, beams have been added to support the deck. The cross beams mark where the hull will be printed in sections for later assembly. The integral foredeck is added. The portholes are located by reference to their position on the original plan. Individual portholes are formed by taking a cylinder that is partially inserted into the hull and then subtracted, leaving a cylindrical impression. In passing, you will note the hull, which was initially a plane with no thickness, now has thickness that will be used in the 3D print. At 1:96 scale, the model is just over a metre long. The height of the build area on the printer is a maximum of 25 centimetres, so it was necessary to split the hull into multiple sections for printing. This is the bow section ready for export from Blender to the printing process. The format used is an STL file. Note the capstan lines embossed into the deck. And for comparison, the capstan lines or scoring on the original ship. I would note at this point that learning any 3D modeling software package is by no means a trivial task. Blender is a highly complex open source package that can produce detailed 3D models and generate extremely realistic video output. It's incredibly capable, but as indicated by its promotional material, the primary focus is on creating striking visual results. While precision engineering style modeling is definitely possible, it's not the software's main strength. If I were starting again, I would definitely consider a more computer-aided design or CAD focused package, which would likely be quicker and easier to learn. As we are moving towards printing, a quick introduction to my printer. It started as a Creality Ender 3. When first sold in 2017, it was one of the most popular FDM printers. I've heard it described as the Honda Civic of 3D printers. Straightforward, reliable, ubiquitous. The function is fairly simple. Filament is heated in the print head indicated and extruded via a stepper motor from the print head to be deposited on the model. Hence the name, Fused Definition Modeling or FDM printing. The print head moves in the X and Z directions, and the print bed moves in the Y direction. So in order to print, it needs instructions on how to move in each of the three directions and how much filament to extrude. There are many other setup considerations, not least the temperature of the print head and the print environment, including the print bed's temperature. But that is beyond today's discussion. So to move from the model file exported from the Blender modeling program to a set of instructions for the printer, a program called a slicer is used. There are various slicer programs available. I happen to use Ultimaker Cura. This is a screen view from the slicer. The model section is dropped onto the virtual build plate and the slicer calculates the printer movements needed to print it. When printing, if there is an overhang beyond a certain tolerance, such as for the upper bow here, then it would collapse under gravity unless supported during the printing process. The light blue supports are automatically generated to enable the printing overhangs. Changing the orientation, the overhead view allows us to look at horizontal cross sections through the print and to see the projected filament path at each print layer. The printer instruction file, called a G-code file, is then exported to the printer and printing starts. The picture is of the final stern section of the model. The supports are clearly visible. I would comment that I was very much learning as I went, with considerable trial and error. Prints often went wrong and had to be repeated with different parameters. In the picture, there are filament droppings on the build plate, where the support didn't work as expected. The hull section turned out fine, but the support partially failed and some filament was printed into fresh air. The hull was eventually printed in 7 separate sections, which were joined together. There are a variety of different plastics available to use in 3D printers. I settled on ABS for this model. The more commonly used PLA has 2 characteristics I was wary of. It melts at lower temperatures, so can potentially deform in a hot car, and it degrades over time when in contact with water. Both might have been okay, but out of an abundance of caution, I went with ABS rather than PLA. ABS is more temperamental to print with. For example, you can just see the layer separation in the center of the picture. I had to reinforce the model to handle this. For later models, I switched to PETG or PETG. It is similarly temperature and water resistant, but has more consistent layer adhesion and, in my view, better printing. The model sections were joined together using overlapping plates. For later models, I incorporated these jointing plates into the print rather than adding them after printing. The extruded plastic from the print head is 0.4 millimeters wide. There is inevitably some roughness in the resulting print. This can be addressed, for example, by using a finer print head, but that brings its own issues, including longer print times. And some of the sections already took over a day to print. Anyway, I found the simplest was to address this by old-fashioned sandpaper and filler. You can see some evidence of this here in the bow, much like the car bodywork repairs of my youth. The prop shafts and props were ordered from Simon at the excellent propshop.co.uk and fitted. The electric motors were set on a removable mounting block that could be substituted if necessary in the future, for example if the motor type needed to change. The superstructure, funnels and other deck items were all modelled in the 3D virtual space, with reference to the builder's plans placed behind the virtual model. Virtually all items, no matter how complex, are created by manipulating a range of simple shapes: cube, cylinder, cone, sphere and torus. To give a couple of examples, the air vent on the right is a simple section from a torus or donut. The funnel comes from a cylinder that has simply been stretched in the middle. Once the funnel has been rotated to the correct angle, the lower part extends below the deck and its base is not parallel with the deck. To get a cut at deck height, a box is created that extends from deck level downwards. This box is then subtracted from the funnel shape, leaving it cut off at deck level. I used straightforward plastic sheets for the decking. A major consideration was how to allow access to the inside of the hull once completed. What I had seen from other models was the superstructure fashioned as a removable section, with raised fillets giving protection from water ingress. However, with the design of Broke, this simply wasn't possible. The superstructure elements are far too small. Instead, I opted to have the majority of the deck removable, secured by small magnets. This worked, but it did leave the vulnerability of an inevitable risk of water ingress, despite the tightness of the joins. When using ABS in particular, one potential technique is acetone smoothing. The model parts are placed in a container with a fan and a paper cloth or similar material soaked in acetone. After about 10 to 20 minutes, the acetone fumes soften the ABS, causing the fine ridges from 3D printing to disappear and leaving a smooth surface. After testing, yes, the model does work, but the results I found somewhat inconsistent. It's simpler and more reliable to use sanding and filling, or even better, to print with a resin printer, which uses a different process and offers much finer resolution. I purchased a resin printer only after completing the Broke model, so this wasn't an option during this particular build. Painting the 3D model was pretty conventional. Initially, marking out the lines for painting using a pencil and a holder, then masking, spraying with an airbrush, including finally the boot topping, seen here partway through the spraying process. Of course, one of the frustrations of only having black and white pictures available is that it's impossible to tell the exact colour of the ship. I had visited HMS Caroline in Belfast, one of the few First War warships still in existence. There has been work to examine her paint colours, with a number of grey shades visible in the layers. There are also, of course, a few forums with detailed discussion of First Warship colours and of the precise colours in Admiralty fleet orders. After looking at this, plus some commercially available model shades, I fixed on a standard Vallejo airbrush grey for the main hull colour. At the same time as producing the plastic parts, I was also developing the control systems. Before starting the model, I had more experience of hobby electronics than I did of modelling, so it was natural to experiment with different electronic systems in the model. The throttle and rudder control is via a standard radio control unit with a joystick that gives forward, reverse, left and right. A mixer program running on a Pi-Pico microcontroller changes the engine speeds to match rudder orientation. A Raspberry Pi microcontroller hosts an onboard Wi-Fi hotspot and web page, which controls the other functions of smoke generation, sound, and a bridge webcam. An attempt to control the gun turret orientation was developed and then abandoned, as was a foray into controlling the motors via Bluetooth rather than conventional RC. So the function of a mixer is to change the relative speeds of the three motors based on input from the throttle and the rudder settings. As the rudder angle increases, the speed of the inside motor reduces and the outside motor increases. The turning effect is amplified. With a hull that is relatively long relative to rudder size, this is essential for maneuverability. This video was of a test in a friend's pool during construction. There are commercially available mixer units. However, the advantages of creating my own were both lower cost and greater control. Ability to set the parameters of how aggressive is the motor-induced turn, and also the overall motor speed. A Raspberry Pi Pico microcontroller provides an effective, programmable, and reliable solution. A H-bridge board then controls the direction and speed of each motor based on the Pico's output. The other functions, beyond throttle and rudder, are controlled via a web page on a tablet computer. A Raspberry Pi in the model hosts a Wi-Fi hotspot. Logging into the hotspot and navigating to the control page gives this display as shown. The smoke generator is turned on and off via a slider. The sounds are similar. A slider for engine noise or a button for the ship's bell, for example. Simple sound files played over an onboard speaker. There is then a micro camera installed in one of the portholes under the bridge. Virtually imperceptible on the model, it can transmit live video feed of the view looking forward. In this case, it is a mock-up to look at the view of a warship seen at sea. The gauges at the top of the display are not in active use. The smoke generator uses a small 20mm disc. This is ultrasonically vibrated to create a stream of visible water vapor. Adding a fan and a 3D printed reservoir creates a pleasing smoke effect. Other enhancements didn't work as hoped. I tried enabling turret control using small stepper motors like those used in camera lenses. Perfectly feasible in the workshop, but a hasty trial ended disastrously. The model was overloaded, took on water, and sank in our local boating lake. The initial decision to have a fully removable deck was, of course, a contributory factor. I continue to muse on ways to improve the water tightness of the model while retaining hull access. The picture of the model looking remarkably clean was taken immediately post-rescue. Lesson learned and turret control abandoned for now. I'd like to end with some video of the model in its intended environment on the water. My thanks to the gentleman who runs the RC Model Warships YouTube channel, who shot the video and gave me permission to use it. It's remarkably hard to control the model and take video footage at the same time. I hope that this talk has given a useful insight into creating a realistic model from original sources using 3D printing. Thank you.